We will now move to the core topic of this course. So, we will discuss Sobolev spaces. These are subspaces of the LP spaces, and they form a natural setting, a functional analytic setting for the study of partial differential equations of many kinds. Okay, so in all that follows, omega contained in Rn will be an open set, and then d omega equals boundary of omega. So, if you have, for instance, a bounded open set, so this will be omega and this will be d omega. Okay. So, definition. Let m greater than or equal to 1 be an integer. Let 1 less than or equal to p less than or equal to infinity. The Sobolev space W m p omega. So, W, there are two indices here, m is for the order, p is for the exponent of the Lebesgue, as we will see in a moment, okay, is defined by Wmp of omega equals set of all u in LP of omega. So, this is where the p comes in. We are in LP space, okay, such that d alpha of u is also in LP of omega for all mod alpha less than or equal to m. So, these are the multi indices, as you know. So, m is the order of up to which you are considering the derivatives. So, u is an LP of omega function. So, it is a distribution and it has distributions of all derivatives of all orders. So, we want that the distribution derivative may or may not be LP function. So, you want to show that they are all LP functions, or if they are all LP functions up to order m, then you say the space is Wmp of omega. So, this is a vector space. So, this is the definition of the space. So, this is a vector space, vector subspace of LP of omega, and we endow it with the following norm. Okay. So, if 1 less than or equal to p less than infinity, then you say norm u m p omega. So, we specify all the parameters. M is the order, p is the Lebesgue exponent, and omega is the domain where we are looking at, and that is equal to sigma mod alpha less than or equal to m and norm of d alpha u LP of omega power p, and then the whole thing to the 1 by p. Okay. Now, you could define it in other ways also, like for instance, you could just define it as sum of the LP norms, but they are all equivalent, and we will see that this is a more convenient way to have it in. Okay. So, this is especially in when p equals 2, this is a good way to write it rather than just a sum, but otherwise you could write, since given is a certain number of norms, norm linear spaces, when you want to associate with it jointly with a norm, then this is, you could do it in myriad ways, but this is the one which you are going to choose. Okay. And if p equals infinity, then you have norm u m infinity omega equals max mod alpha less than or equal to m of norm d alpha u L infinity of omega. Okay, now this max makes sense because we are only taking the maximum over finite number of components. So this is the space and this is the norm. Okay, so now we have some notations and conventions. Okay, so the first one, if P equals 2, then it's somewhat special as we will see. So we write Hm of omega equals Wm2 omega. Okay, so instead of writing P equals 2, so we drop the index 2 and replace the W with a H. H is for Hilbert, and therefore we will see that in a moment. Okay, and the corresponding norm, we will say norm M omega will be stand for norm M2 omega. Okay, so the norm M2 omega, so this is just a slightly shorter notation. So we drop the index P, the parameter P, which is equal to 2. So if this only 2 indices appear here, then it's just the order and the domain, because we know we are in L2. Okay, so this is the first one. Now in this case, we have an inner product of, so uv in m omega is equal to sigma mod alpha less than or equal to m of integral over omega d alpha u d alpha v dx. So both are L2 functions, so you can integrate, and then that gives you an inner product, and we are assuming without loss of generality that we are all real valued. Okay, so we are working in over R for. Okay, so this gives you the norm. Okay, norm uu square will be precisely the norm which we define for P equals 2. Okay, so this is the norm when P equals 2. So you get sigma norm d alpha u square equals norm u square, and that's precisely what you will get when you put u equal to P. So this, you have an inner product space in this case. Secondly, we define semi-norms mod u mp omega is equal to just the highest order derivatives, mod alpha equal to m norm d alpha u in Lp of omega power p whole power 1 by p. So if u is in Wmp omega. So again, if p equals 2, we have mod u m omega, which is equal to sigma mod alpha equal to m norm d alpha u in L2 of omega whole square power 1/2, and u belongs now in Hm of omega. Okay, and if so, this is for 1 less or equal to p less than infinity, and you have mod u m infinity omega. Well, that's yeah, is equal to max norm d alpha u L infinity of omega mod alpha equal to m. So we are only looking, so why are these semi norms? They have otherwise all the properties of the norm, except when this quantity is 0, it doesn't mean that the distribution is 0, because if the first derivative is 0, for instance, then you know it's only a constant, and therefore you do not you don't get it that it's 0. So these are only semi norms. Okay, then for consistency, we denote Lp of omega equals 0p omega. So if m, that is m equal to 0, we have defined m greater than or equal to 1 in the Sobolev space. Now we will see later why this is consistent. So the LP is just the case when m equals 0, that means no derivative is used, okay. So that means just a function, and if you look at the definition of the norms and so on, that's precisely corresponding to mod alpha equal to 0, and that is alpha equal to 0, and therefore LP of omega. So henceforth we write mod u 0 p omega for norm u in LP of omega, p not equal to 2, because mod u and norm u are one and the same, because that is the highest order you are anyway taking, and therefore whether it's mod u or norm u it doesn't matter. So this is equal to norm u 0 p omega, okay, and this is the norms we give for the LP omega to be consistent, okay. And if p equals to 2, so this is u in W MP omega, sorry, in LP of omega. If p equals 2, so if u is in L2 of omega, then you have norm u in L2 of omega will be written as mod u 0 omega. So this is the these are the definitions which we want to keep, notations and notational conventions which we are doing. Okay, so now if you take u in WMP of omega, sorry, 1p of omega, that means, so what is this? This means u and all its first derivatives are in LP. Okay, so now I am going to map it to the following thing. So that is u du by dx1 du by dxn, and this therefore belongs to LP of omega power n plus 1. So when you have n plus 1, you can put a product. So this means that norm u MP of omega as we define is, so let us call this as TU, say for instance, okay. This is the same as the norm u as norm of TU in LP of omega power n plus 1. So this mapping, the mapping T is an isometry from WMP of omega into LP omega power n plus 1. Okay, so this tells us the first theorem which we want to do. The space W1p of omega is complete, so it's a Banach space. It is reflexive if 1 less than p less than infinity, separable if 1 less than or equal to p less than infinity. In particular, H1 of omega is a Hilbert space because it's a complete inner product space. Okay, so proof. So let un, so what do we have to do? We have just show that every Cauchy sequence converges. Okay, so let un be Cauchy in W1p omega. Okay, so then this, what does this imply? From the norm, so that means norm of un minus um, yeah, that's okay, 1p omega, okay, is less than epsilon for all nm greater or equal to capital N. Okay. So what is this? So norm un minus um 1p omega power p is equal to norm un minus um in LP of omega. I am still using some notation till we get somewhere. After some time I will stop. Okay, power p plus norm d sigma I equals 1 to n du by dxi n minus dum by dxi in LP power p, and that is going to be less than epsilon for all nm. This implies that un is Cauchy in LP of omega and dun by dxi Cauchy in LP of omega for all 1 less than equal to I less than equal to capital N. So LP is complete, so un goes to some u and dun by dxi all converge to some vi 1 less than equal to I less than equal to n in LP of omega. Now what is the meaning of the distribution derivative? So let phi belong to d of omega, then what do you have? That integral dun by dxi phi dx on omega equal to minus integral on omega un d phi by dxi dx. Now I want to pass to the limit. dun by dn converges to dxi converges to vi in LP. Now phi being a C infinity function with compact support will be in all LP spaces, in particular in the dual space of LP, and therefore, and that's a fixed function. Therefore I can pass to the limit. So this will converge to integral on omega du by dxi phi dx. And in the same way, this side du un vi. Okay, du1 dxi goes to vi. Now un goes to u and d phi by dxi is in C infinity function, fixed C infinity function with compact support, which is in all the duals in the dual space, and therefore this goes to u d phi by dxi dx. And this implies that vi equals du by dxi. So this means that u itself belongs to w1p of omega because all its derivatives are in LP, and consequent, and un goes to u in w1p of omega. Because un goes to u in LP, dun by dxi goes to du by dxi in LP, and that means un goes to u in w1p of omega, and this implies that w1p omega is complete. Now you take the mapping T from w1p of omega to LP omega power n plus 1 described above. So Tu is equal to u du by dxi du by dx1 comma du by dxn. Now this is an isometry. So image of T is a closed subspace of LP power n plus 1. So a closed subspace will inherit all the reflexivity and separability properties of the original space, and an isometric isomorphic image of reflexive space is reflexive, separable space is separable, and therefore this implies that w1p omega is reflexive for all 1 less than p less than infinity and separable for all 1 less than or equal to p less than infinity. So that this comes from the inheritance properties of that. Okay. So remark. So we have something useful from the proof which we have seen above. So let us assume that this is a very useful technique which we remember. Okay, so let un be a sequence in W 1p of omega, and let un converge to some u in Lp of omega. Let dun by dxi be bounded in Lp of omega for all 1 less than equal to I less than equal to n. Okay. So now if you take 1 less than p less than infinity, then W1p omega, Lp of omega is reflexive, implies there exists a subsequence. You can choose a common subsequence for all of them, they are only finite number, such that dun k by dxi converges to some vi weakly in Lp of omega. So now let us again do what we did in the theorem. So you have integral d unk by dxi phi on omega dx equal to minus integral unk phi d phi by dxi dx over omega. So now you have a weak convergence, and phi is in the dual space a fixed function. By definition of the weak convergence, this goes to integral omega vi d phi by vi phi dx, and therefore that is equal to minus integral over u. This converges as before to u, and d phi by dxi is in a dual, and therefore you have d phi by dxi dx. And consequently, once more we see again that du by dxi equal to vi. Okay, and this implies that u is in W1p of omega. So un converges to u in Lp, and all the derivatives are bounded in Lp. Itself says that the limit is in W1p. So you are able to get a lot of extra information from this. This is a very useful observation. So if p equals 1, L1 of omega is separable. So if something is bounded in the dual space, it will have a weak star convergent subsequence, and therefore same argument holds using weak star convergent subsequence for W1 infinity omega. So if you have un converges to u in L infinity, and all the derivatives, first derivatives are bounded in L infinity, then you will get that u itself is in W1 infinity, and this is again very useful. So we are able to predict when a function will belong to this thing. Okay, so then another remark can extend by induction these results for all m greater or equal to 1. So, in most of this course I will only prove results for m equals 1, sometimes I will prove for other m also, but most of the time it will be clear by iterating the arguments. You can go on to higher and higher orders of the spaces. It is just technically more horrendous, but otherwise no new ideas are involved, and therefore we will do that. Okay. So, now important definition. So, we know that d omega is contained in LP of omega, and for d omega the distribution derivatives are just the classical derivatives, and therefore they are also C infinity functions with compact support, and in fact d omega is contained in contained in WMP of omega for all m. Okay. So, now comes the definition. We denote WMP 0 omega equals WM d omega closure in WMP omega. So, this is the closure in the WMP omega norm. So, if you take that closure, so this is a closed subspace of WMP omega. So, important question which we will not be able to fully answer, we will answer partially. So, question, WMP of omega is a strict subspace of WMP omega. So, we will take some time to answer this question. We will soon answer it in the case of Rn itself, but for open sets we will answer it after some time. Okay. Okay, so now the some notations for case P equals 2 and omega equals Rn. Okay, so now if P equals 2, then if you look at Hm of Rn, this is set of all u in L2 of Rn such that d alpha u is also in L2 of Rn for all mod alpha less than or equal to n. Now, on L2 we have the Fourier transform. Okay. So, and the Fourier transform is square integrable, and by partial theorem the L2 norm of a function and its Fourier transform will be the same. Therefore, and you also know that d alpha u hat xi is nothing but 2 pi I to the mod alpha xi alpha u hat of xi. Okay. So, this is for xi in Rn. So, if you have u is in Hm of Rn, implies u is in L2, u hat is in L2 of Rn, and xi alpha u hat xi is also in L2 of Rn for all mod alpha less than or equal to m. Okay. So, and so this is, and the converse also true, and consequently you have another way of looking at this space. Okay. So, now if you look at 1 plus mod xi square power m, and you look at sigma mod alpha less than or equal to m of mod xi alpha square, the same powers of alpha of xi occur in both. So, this implies there exists m1 greater than 0 and m2 greater than 0, which depending only on the dimension and small m, okay, such that m1 times 1 plus mod xi square to the m is less than or equal to sigma mod alpha less than or equal to m mod xi alpha square less than or equal to m2 times 1 plus mod xi square to the m. Okay. So, consequently, we can so therefore, we can equivalently define Hm of omega equals set of all u in L2 of Rn such that 1 plus mod xi square to the m by 2 u hat of xi belongs to L2 of R. So, this is just the same as this statement. They are equivalent statements and therefore, you can write it this way. And using the Placherel theorem, this implies that an equivalent norm in Hm of omega is, and we will denote it by the same symbol, we will not give it another thing. So, you will have norm u in m Rn square, Hm of Rn, sorry, equal to integral over Rn 1 plus mod xi square power m mod u cap xi square d psi. Okay, so this is another way of writing the Hm of Rn when p equals 2 and its norm. Okay, so this is another equation. Sometimes we will find that this is useful to know. Okay, so we asked this question, is WMP 0 of omega the same as WMP of omega? So we will answer that question in the affirmative for omega equals Rn, which we will do next time.